Thank you. So, hello everyone. I am Eric Dupont. I am a research engineer at TTF R&D on atmospheric flow modeling at mesoscale and microscale, especially regarding the wind resource assessment tools and methodologies. I have been involved in the POWSEIDOM project and now in the project NEMO to follow up this project for EDF. With my colleague from EDF Renouvelables, Cedric Dall'Ozzo, who will speak after me. So in my presentation, I am going to show briefly how the outputs of these two projects could be used in the future by EDF. First, we know that there is a need to improve the accuracy of the turbulence intensity measurements using LiDARs, especially to address this problem of interbeam cross-contamination effect, which can lead to an over or an underestimation of TI. And the variance method that has been developed in the framework of POWSEIDOM, combined with the noise filtering, has the potential to improve the quality of the measurements, and it could be applied in the future at EDF, providing that the commercialized LiDARs include at least 6 beams, which is the condition for this variance method to be applicable for every wind direction. For offshore applications, there is a strong need to be able to measure turbulence using a floating LiDAR. We have seen that two methods have been developed to correct the turbulence measurements from the buoy motions, one based on the spectrum of the line of sight velocity and one based on the geometric correction of the instantaneous measurements. And both methods could be very useful in the future, providing additional validations against reference measurements. And another useful deliverable of POWSEIDOM project was the 1-year LiDAR dataset obtained at Île du Planier in the Gulf of Lion in the Mediterranean Sea, which is an area of future development of floating wind farms. It includes different turbulence variables, which can be used as input or validation data of numerical models. And moreover, the detailed analysis of this data set that has been performed in POWSEIDOM project is very useful in characterizing the processes which take place in the marine boundary layer near our coast, which are very complex regarding, for example, the diurnal and seasonal variations of the thermal stratification and of the low-level jet occurrence and so on. And there is also the need to be able to model correctly the turbulence in order to get information on its horizontal and vertical gradients, and also to get long-term time series, which means that this is necessary to find a good balance in the modeling configuration to keep reasonable computing time. And some important questions are currently addressed in the NEMO project. First, there is a question about the relation between the turbulence variables that can be provided by a mesoscale meteorological model like WRF and the current reference, which is the TI measured with a cup anemometer. Another question is the impact of the horizontal resolution in relation with the selection of the turbulence model. Especially, do we need new turbulence models able to model turbulence in what is called the gray zone? And it's important to evaluate the ability of these models to provide a reliable estimation of turbulence intensity. And finally, the NEMO project will allow some comparisons between mesoscale simulations and other data like LES simulations and scanning LiDAR measurements. And these comparisons will contribute to the validation of these mesoscale simulations. So now I let the floor to Cedric.
Hello, everyone. So yes, so my name is Cedric Dall'Ozzo. I'm working in EDF Renewables, so in the offshore wind engineering team. And so today I just we try to to give some feedbacks or needs or perspectives more on developer side. So regarding the Poseidon project, so it was a quite important project for EDF Renewables, especially in the context of French offshore tenders, so in the Mediterranean Sea. So and especially in the context of deep water in Mediterranean Sea. So of course we know the impact and the importance of the turbulence intensity for different topics related to energy yield assessment, like for wake effect, where the turbulence can lead the dispersion of the wake behind the wind turbine, or for wind turbine performance, also through the impact on the power curves, for example. But it is also quite important also for floating wind, and especially for floating foundation design. And so in Mediterranean Sea, there was a lack of measurements, I want to say, or fixed offshore measurements. To characterize at the end the turbulence intensity in Mediterranean Sea. And so, the LiDAR deployed in the POWSEIDOM project on the Planet Island was quite important, and appears as a reference at the end in the Mediterranean Sea to characterize, of course, the wind condition, and especially the turbulent intensity, and especially with the different improvements of the prototype installed on the island with higher frequency measurements. So yes, very interesting point from a developer point of view. Yes, another point. So of course, unfortunately, ground-based LiDAR, or I mean TI measurement from ground-based LiDAR is not well accepted in the industry. So this is still the cup anemometers, which is the reference, especially in the standards for turbulence and turbulence intensity measurement. So we highly need correction methods at the end to be able to use the turbulence intensity and to improve the acceptability of the turbulence intensity measured by the ground-based LiDAR. So yes, I think it was also very interesting to see the different developments presented just before by Maxime on this point, for example, through the variance methods, which appears as quite a promising approach for the correction of the turbulence intensity measurement. So yeah, and of course for floating, for offshore development, usually we developers install floating LiDARs, and when we want to work with floating LiDARs, we add another level of perturbation of the measurement due to the buoy motion of the floaters. So of course I think we need also correction algorithm for or motion compensation algorithm to correct at the end this motion of the floating LiDARs. And once again, I think the Poseidon project and NEMO project to try to answer to these needs. And so yes, it is quite interesting for EDF to follow this project, and to learn also what could be at the end the different sources of error regarding the turbulence intensity, and to see how we can correct at the end this turbulence intensity using ground-based LiDAR and floating LiDARs. But for both technology, I think it is quite important also to have some correction methods, so well accepted, potentially included also in some industrial standards like IEC standards or other standards. So yes, it is quite important to at the end to get yes, correction algorithm, but validated correction algorithm and quite well accepted by the industry. And so another very interesting point is also the different work regarding the dual Doppler scanning LiDAR. So as you know, I think this technology is quite well accepted in some countries, like for example in Japan, already included in Japanese standards, for example, for offshore development. And so it is quite important also for us to see what could be the ability of these devices to assess the turbulent intensities. And for that, I think it is quite important to follow and to be involved at the end in the measurement presented just before by Julia regarding the test on the Blythe site. And so yes, maybe a last word regarding the quite important needs also that we have on numerical side. So of course it is important to mention the measurement, but we need also to improve also our comprehension regarding the modeling, the numerical modeling of the turbulence intensity. So as Tanguy presented previously, I think there are different metrics, and we have to understand also what could be possible to extract at the end the turbulence intensity from other turbulence metrics, which come from numerical modelization. So it is quite important to us to have access to different approaches which could help us at the end to characterize this turbulent intensity, and especially for different topics. So yes, for vertical extrapolation, horizontal extrapolation, and to understand maybe a bit better the behavior, for example, regarding transition land offshore, for example, which could be quite interesting for some project near shore, for example. So yes, I think that's all for me. But just to maybe a last word, just to say that at the end, POWSEIDOM and NEMO, I think try to answer to all these different issue or problems that we could have on the developer slide. So so thank you for all this work realized in POWSEIDOM and NEMO project.